Thank you so much for being here today. We are going to have an interesting session. Today, as you are aware, we are going to be doing a workshop on the REVEN platform. So as opposed to last week where we did a demo of the features of REVEN, today we are going to give you access to the product, so you'll be able, through guided exercise, to get hands-on experience about what this is about and how it works and all of that. Before we start, though, we have a few things to cover. So let me go through my slides. Yes, of course, customer thing. About me, I'll be your speaker today. My name is Matthew. I've been working at Tetrane for 8 years now, and I'm partly involved with the development and also with more customer-facing things like demos and labs and trainings, and that's why I'm your speaker today. But I'm far from alone. We have a few people on the chat, namely Mark, who's our CEO. So if you have business questions, he's your guy. And then we also have Quentin and Florent, who are fellow R&D engineers at Tetrane. And they will be here to help me answer questions you might have on the chat. And also, they will provide support if you have an issue with the lab setup, because we will be giving you access to virtual machines with REVEN installed. But if you have an issue with them, just send them a direct message, and they'll be able to help you out. And also, Florent and Quentin worked on the VM infrastructure that we are going to be using today. So thanks a lot for them. Thanks a lot to them. And as I mentioned on the chat, on the Zoom chat, we won't be using the Zoom chat, especially now it's all filled up with weird messages in Spanish. We will be, yes, thank you for the Discord handle, Skia, because Skia, Florent names is Skia on the Discord. We won't be using the Zoom chat, we'll be using the Discord, so please join there. If you haven't already, we won't be monitoring too much the Zoom. I have it somewhere, but it's much less practical to use. Now that this is over, so as I mentioned, we are going to be doing a workshop today. So before I give you access to the virtual machines, I'll show you a few things. Last time I showed you the features of REVEN, how they were supposed to be used, and the kind of data you could extract from a trace and all that. And now I'll be trying to teach you how to use it, actually. So I'll be spending a few minutes showing you things around. So first you get a refresher, and also because I'll be more focused on how to use it as opposed to the kind of data you can get. So I'll start with that. I'll start with showing you a couple of things on how to manipulate the UI. We'll start with that. Then I'll give you access to the virtual machines, and you'll be able to start the exercise. Today, we're going to be focusing on two exercises. We'll have a sample program, which I made in order to give you first approach with REVEN. So the program is really not a real use case. This is something I built for the sole purpose of teaching people how to use REVEN. So we have if you look at the program and what it does from a user perspective, the program is actually doing some pretty maybe stupid things, but that's normal. My goal here is really to get an environment where we can explore features of REVEN and show things and discover and get used with the tool mostly, because what we'll learn in exercise 2, we will use in exercise 1, we will use in exercise 2. And exercise 2 is an actual CVE inside the driver, inside the TCP/IP driver, and we will be looking and getting some answers of that. So it's a recording of a proof of concept made by a Quarks Lab security company in Paris, and so we'll be looking at the recording of that and trying to get information about what the exploit is about, and again, see the kind of information we can get from such a trace. We should do that in the 2-hour time span, so that's quite short, and I'll be getting you from zero experience to actually getting answers about that CV in the kernel. So hopefully it will happen in the process, but that's still a pretty short time span. So hopefully we will be the exercise I'll give you are pretty guided. So hopefully everybody is going to be able to follow along, even if you don't have experience in the Windows kernel. That's okay. The exercise gives you locations in the trace and everything, so you can follow along. We'll be going through some Python as well, but it's more like fill in the blanks, so you won't have to actually sit down and type a whole script. At the end of that, we'll have a special little Tetrane bonus. So stick around for that at the end. And for those of you who want to explore a little bit more and have more time, if you want, there's an encore. So the Zoom session will probably stop at that point, but we will hang on in the chat and the virtual machine will stay up. So if you want to explore the 2 exercises, you will be able to after the session. And also there's a third trace about another CVE, and we have a few questions that might guide you in your analysis of it if you want, but that's really something completely free. There's no exercise there, so really additional content for those of you who may want more at the end of the session. I'm monitoring the chat. If you have questions on the Discord chat, please post them there. I'll be able to answer them. If I'm able to answer them, I will do so orally, or my colleagues may also answer them by text or provide additional context or stuff like that. Yeah, not a tour of the product. The slide isn't quite up to date, but I'm interested. I want to show you a few things about REVEN before we start, okay? So first of all, when you get your access to the virtual machine, what you will get is this. You'll get 2 buttons, Python API, that will take you to the exercises. This is a Jupyter instance. Jupyter is a REPL environment for Python, but we also use it to push the exercises. And the first exercise will be lab start. So you click there, it will open your notebook, and you will get this, which is our first guided exercise. Jupyter is composed, a notebook is composed of cells, and you can execute cells by selecting them and pressing Control Enter. Most of the time you won't have to because we won't be doing much Python, but if you tend to double click somewhere to select a word, it will activate the markdown view. So again, Control Enter takes you back to that view. So just keep that in mind, double click, Control Enter. Okay, so you'll be reading the exercises, and also on a trace, you will start with the guided tour. So please do that small tutorial. It's 5 minutes long tops, and it will give you all the little tidbits that you need to be able to find your way around in the GUI. So please don't skip that step. I think the first exercise, I'm pretty sure it mentions that you have to do it. Please do it. It's just a huge time saver at that point, especially since we're trying to compress all that in the span of 2 hours. So please think about that. And obviously, the other link is that GUI that I just showed you. And as I said, by default, it opens up the tutorial. What did I want to say? What did I want to mention here? So hopefully you've seen last week's either lab or the video of it, but you should be aware that this is our trace. We recorded the entire virtual machine for a certain period of time, and this is the trace of execution, and we have access to the context of the VM at any point in time. So whenever I select an instruction, the widgets, they get updated, but we have to remember there's each instruction being executed here takes my virtual machine from one state, to another state. So that's why we call that a transition. And you have access to both states, the state before that instruction and the state after. And obviously the state after that instruction is the same as the state before that instruction. And you can see that, for instance, in the CPU view, there's a state before and after, and I see, for instance, yeah, RAX changes, its value changes, which makes sense, so we highlight it in yellow. That works too with memory. If I take a memory operand here, and I open it up like that, you will see the content. By default, we show the content after, but I can also switch back to the context, to the content before. So you should see, we highlight in yellow when there's no blue highlight, and you see the value changing. So we really have this notion of context before and context after, and that will make a lot of, and yeah, sometimes you have to keep that in mind. For instance, when I show a memory operand here, by default, we show the context before. So that's what I see here. It's not the same value, but if I show the context before, this is the same value. Okay, so that's my trace. We can view the context, we can explore memory, I can open up every location in memory, and I can view operands. About that little tooltip, by default, it shows, like for a register, it will show the value. And we allow, if that value is a memory, whether or not it's a valid address, we allow you to click on it and open that as a memory address. In that case, it's not a valid memory address, but we still give you the option of doing so if you want to. And the same is true for the memory operands. the first value here is actually the address. So that's RSP plus 240 hex equals that value. So if I open that up, we know that's a memory operand because we know that's a memory address, sorry, because it comes from a memory operand. So by default, there's no pop-up. But here we also allow you to open the content of that as a memory address. So if we click that and open that, again, that's not a valid memory address. So by default, that's the content to the right, and again, content to the right, and that's the address to the left. Just remember that that's because it can be a little bit confusing when you are when you're manipulating the GUI, and I'm really trying to give you small tips so that you can navigate easily. I hope you're all following around. Let me know if I'm just going too fast because you just got there and you need some more context. But otherwise, I'm going to assume that you saw last week's video and you kind of have an idea what we're talking about here. Let's go on with navigation. The most important tool in navigating such a trace, which we are going to use a few times, is the percent key. The percent key takes you basically from a call to a ret, or from that ret to the call in the trace. So if I have a call there, I can press percent and go to that ret, and I can see the return value at that point is 3BFFD. Okay, so 3BFFD, and if I'm there, I selected the ret, I go there, I go back to the call. But that doesn't work, and that only works if I select the call. If I'm inside the function, I can't do that. I need to use the backtrace, double click there, and then press percent, because double clicking here takes me back to the call, which I selected here, which is something that you don't get in obviously in a debugger, because you can't go back in time. But that takes me back to the moment where I did that call. So if I want to look at the arguments of a function, double clicking here and looking at the register will give me information. In that case, RCX, what is that call? No, A2I, yeah, let's go to A2I. The first argument is a memory operand, so I can just double click there, and that's the value I'm interested in. Actually, that's a string, so it's displayed a keyword. It's not interesting, but I can change that US byte, and I will get the string in question. Okay. So percent takes you to the right, takes you to the call. If you use percent on other values, like maybe a push, most likely a push, it should take you to the pop, corresponding pop, because again, the goal of that shortcut is to take you to the corresponding instruction in the trace when that makes sense. So for a push, it's a pop, for a syscall, it's a sysret, and for a call, it's a ret. But most of the time, you're going to be use that on call ret. Yeah, so that's for navigation. So I can use that to navigate there. We've also looked at the memory history last week. You can access the history of memory that is selected here by checking that that label here, and that's the history of the selected region. And you can double click somewhere, it takes you to that trace. That's quite consistent with the rest. And for navigation, the thing I used last week as well was the timeline. Here we will push search results. Like if you search for a certain call being called in the trace, like in my program, I want to see calls to printf. So click there. Okay, there's a single result. Can go there using next. That's the result I'm interested in. You can look at the arguments if I want to. And it is located here. But I can use that to navigate the trace and just seek randomly if I want to. Or I can use that to jump to a certain transition. Like I want to jump to the end, I just enter a big enough number and I'm exactly at the end of that trace. One thing you're going to do that's almost sure, when you click like that, it's very easy to do left click drag. And left click drag is how you zoom in the trace. Like if that result is pretty hard to see because it's very close to the beginning, but I can zoom in and I see my result here. So that's the zoomed portion of the trace, which you can be seen here as white. If you want to reset the zoom, just Control-0 resets your zoom. Because you're going to do that. Yeah, it's zoom in, it's hard to see, just Control-0, or Control will also zoom out if you want to. Yeah, I think that's enough for now. You can go back in your trace like you would in a browser, or forward. Same thing with the hexam. You can go back to previous addresses you opened. And yeah, that's enough for now. So about that trace, that the first lab trace that we're going to have a look at. This is a simple program that takes an input and then does things depending on that input. And in that case, it crashes, which is what we see here. We have a divide error, and that's where I stop my trace. Okay, so if we go to the very beginning, that is the call to main. And if I go to the end, that is where my trace crashes. But we still have everything on the virtual machine. So if I look, there will be kernel code somewhere. There might be other processes running at one point. It's just that the beginning and the end of my trace are centered on my process. So I can use that as easy starting point. And that's what you're going to be doing in the exercise. In that case, the start of the exercise will be trying to understand where that value here. So we do a division by 0, which I see here. That's my address, RSP plus something, and that's the value contained. That's a 0. And we're going to try to understand where that 0 is coming from and use the various tools REVEN provides to do so. So you're going to be doing that in the exercise. We're going to be doing that in the exercise, yes. And what else did I want to mention already? I think that's good. What is that trace? Yes, we just talked about that. Percent, memory history. Okay, I think we got everything. So we'll give you access to the virtual machines now, and you can start. And so you're going to need your email. Let me switch back to where I was. There we go. Okay, so if you want to get access to your virtual machines, you should use that. Come on, you should use that URL. Maybe I should actually try to copy that over to the Discord chat. Let me do that. Okay, so I passed the URL over to the Discord chat. Use that address, and you will need your email, your registration email, and this in turn will give you access to the page that I showed you a minute ago, that page right here. Okay, and you should go over to the Python API again, OpenLab start. This is our first exercise. We'll see then for the next one. And and you'll get the basic of a navigation. Usually, before every part of the exercises, I will show you how to use things first orally, and then the exercise by text should take over and show you kind of the same things. So a little bit of redundancy here is actually not a bad idea, because it makes sure everybody, it helps me making sure everybody follows along. And each exercise is separated in 2 parts. And usually I will leave you alone to do the first part, and then we'll sync together and I present what you should have seen, and we can move on to the second part. So what I'm going to do, and it's really cool if you guys can follow along with that. I'll post a message on the chat to which you can answer with an emoji, with a reaction GIF, and like press thumbs up to tell me that you're done with that part. So I know that everybody, or at least most people, have finished that part of the exercise, and we can move on. It's important that we kind of work in lockstep, at least a little bit there, so I can make the presentations for the next part and not just drown you in information all at once. Okay, guys and girls, I think it's been a little while, so we should be able to move on. Don't worry if you haven't had the time to do everything. You should be able to just keep going with that first part if there are things that you wanted to explore a little bit more. Otherwise, the next part will be again very guided. We've had a question. If you messed up the UI, I think, quitting the GUI with the little arrow, or if I quit, there's no arrow, if there's no cross, should just restart the GUI, so it should work. What else did we have? Yeah, you can we see a registered value in different formats? So right now, you in the version that you are using, you can't, because the lab is not yet up to date, but in the version that's coming out in next week or so, we will, because we just we had that feedback earlier, so we added that to the project as well. You zoomed in on the text and changes the UI. That's strange. Okay, we'll have a look at that. And one thing I had not mentioned was that you should activate the default session if you want synchronization. That's interesting. I think I just, okay. Yeah, okay, cool. Interesting shortcut. Yeah, in the GUI here, here by default it's not synchronized, but if you sync to default session like so, then in the lab you are able to click somewhere, and that's super useful because then you can go over, you can use that, and it takes you to the right transition, which is again our timestamp or moment in the trace. So I think that's a very interesting feature that you really are going to use during the rest of the exercises, because right now the trace is pretty small, but it will get bigger as we go on. Okay, so you should have had a first start how to manipulate the GUI, okay? And now it's time we get some actual results there. So you should have looked at that pointer here at A to Y. For instance, you could do that. I think I showed you that earlier. And by showing the memory history, you will see how it's used in in the program. And for instance, you will see also that we detect that this is a string, and that's the optional part that I talked about. You can actually filter. So I'm displaying here the string widget, which you can do in View Strings widget. And yeah, you can look for strings like this, for instance, like that. Go. And this will filter all the strings that were found during the trace, and double clicking on some trace, you can get the list of accesses. One important thing here about the strings is that this, interesting, my backtrace is, so what I'm showing you here is a beta build of our next version. So apparently there's a small issue with the backtrace, that's interesting. What the strings are is really, we are monitoring the trace when during the replay phase, which if you remember is when we build indexes for extract data and build indexes for them. So when we do that, we do look at everything, at all the memory accesses. And if a memory access occurs on something that looks like a string, then we log that in the database and we give you access to that. So that's what we have here. This is the entire database of all strings that we detected in the trace, and we can search for them. So it's different from strings in binaries, because there might be a string in a binary that's loaded, but that's never accessed. So we are not going to give you access to that. You should search inside the entire memory if you want to do that, and this is something possible through the Python API. But still, by default, we just restrict our search to what's accessed, and because that's relevant in your trace. Okay, so if you do that here, you will be able to see quite a lot of things, especially here, the output of the printf, which you should have searched for as well. And you could do that with many things, like URLs that are built, or whatever message you see. This is a very good way to find an entry point in a trace. Like if I want to see where the input call is, I can double click here, get the list of access. So I double click on an access, and looking at the backtrace, I see I'm inside the call to printf. So that's a super easy way for me to get an entry point in my trace if I have an idea of a message that appears on the screen in the frame buffer or something like that. So that was optional, so that's why I'm covering it right now. Next part of the exercise is going to be using the taint. So let's go to the end of the trace, because we want to start with the crash, and as I said, understand where the crash is coming from. And that's like the use case for REVEN. You want to find answers about something that happened in the past, from a point that you found somehow. You found that entry point in your trace. Here it's a crash. It's easy, that's the end of the trace, but there are many ways to find different entry points in the trace, and then you want to find answers about how you got there. And obviously, since we're doing timeless analysis, we can go back, but with the tools that we have, we can get information and answers super fast. So the first thing here is, yeah, I want to see what's going on here. So I can open up the memory. I open up that address here, and using the memory history, as I said last week, we can go back to the previous write, like so. That's where my previous write is, and I see that my value is coming from RCX, and then RCX coming from here, which is a different location, and I can do that and find the different places where my value is coming from manually. But I don't want to do that manually. I want to do that using the tainting engine. Okay, so let's do that here. Let's go over and select that region here, right, like so, and paste it here. So that's how you start the taint. You have the taint widget accessible again through the view taint analysis here. So you get that tag 0 and tag 1 are things you are going to tag, so that you are going to taint. And usually we just use tag 0. We don't care about tag 1. And you'll be entering things. So you can enter a register like that, or a memory region. And in that case, my memory region, I just created it by right-click here, copy current address range, and that copies it in a text format that is compatible with the taint widget, and paste it here. And I want to taint that starting from where I am, so around here, and I'll talk about that in a second because you have to be careful about your starting point. And then to the first transition, I want to taint that backwards. I want answers about the past. Okay, so taint. That's how you start it. Yeah, we get a message because taint resulting backwards might be a little weird to look at, but it's going to give me the same answers as before. It's coming from RCX, and RCX is coming from, well, RAX in that case, like right here. And then RAX, we see that we lose the taint on part of RAX because, yeah, it's interesting. We just zero extended RAX, so now we only care about the first 2 bytes of RAX. So really, this is AH, I think. And that AH goes to our CX or CH. And when we do that, we can look at the values. And this is really important because last week's example, the value was just moved from one place to another, but here it's really changed. So we need to keep an eye on the values to understand what's going on. So there, our CX is coming from there. Yeah, it's not going to change through register, but there, so we have a 0 extend, and then there's an LEA. So that value was multiplied by 4 and then added something, and that was coming from there. So there I go from, if you look at it, I go from that value, which should remind you what we found at the result of A2A. And yeah, you'll go from there. The one thing I wanted to mention about how to start the taint is, by default, when you select a transition here, you can go to from current transition, and that selects that transition which I have here. If I want to start it from here, I click there and I redo that. So I do from current transition, and that changes it again. You have to make sure that the starting point here, you update it when you do multiple taints, otherwise you'll have nonsensical results. So if you have a result that you don't understand, please double check your starting point and ending point of the taint, especially if I had started it here. So that's my value, right? That's the address I'm tainting. Okay, so that's the destination operand. If I do that from here, current transition, you see that my taint yields completely different results. And it's telling me that it's coming from that RCX. And that's because we start the taint from the context before the instruction. So at that point, my value isn't coming from RCX because I am like here. So it's coming from there. Okay, so if you select a transition, just be careful about that, because the taint will start before the instruction was executed. And if that matters to you, then that might be a problem when you're going backwards. So just keep that in mind. When you're going backwards, you're going to use the context before. So in my case, it makes sense to start my taint from here, which is after I wrote that value, or even just from the crash, which makes a lot of sense there. That's where the value appears. I start from here, and I don't have to worry about anything. Okay, so that's how you start a taint. And the result we see here are, I mentioned it, where the taint is lost and where something gets, so when something gets untainted and where something gets tainted. So in that case, that memory is untainted and the RCX is tainted. So my taint moved from here to here. But there are places where it's empty, like that, like RCX is empty. And if you look at the state at that point, or yeah, that's not a good example. Maybe it's a better one here. Yeah, at that point, there's no taint, and suddenly RCX gets tainted. That might look weird. That's because we do optimization at the block level. So really, don't worry about these strange results. And that was the warning message I showed there. If you see strange thing, it's just because we do optimization and there are, information that gets lost in translation somehow. But the taint is right. It's just that we optimize things away so that they don't appear anymore in the taint, right? So don't worry too much about that. I got a question. Yes, please shoot. Okay, I'll wait for your question. Let me look at my notes. That's what the taint is anyway. And if you remember last week, I showed you that graph, and that's so where we are right now. I'll I'll look at your selection. I'll look at a question in a second. We are here at the crash. We have our observable value, and we are tainting it, and we are tainting it backwards. So we will be moving back to the source, and that's what you're going to be doing in the first part of the in that part of the exercise. You'll be going that, and then you will be tainting forward, going from the source to other copies, potential copies of that value. Okay, so you'll be doing that in the exercise. So Fu, something, you got a question. So from the current transition, after you have selected, it didn't change the tag. If you want to trace a certain register value, you should just edit the, like, let's say I want to taint RCX from here because it's one of the sources, it's valid as well. I just type RCX. The tag is what you want to taint, and the from and to, or current transition, is where you want to taint it from. Does it make sense? Yeah, okay, cool. So yeah, if I want to taint, I just can taint RCX or just CH if I want. CH, does it make sense? Yeah, CH. So that's 0, the first 2 bytes of RCX, which is what we saw here. So yeah, I can do that either manually or just, if you tainting memory, it's much easier to just copy the address range. But if you understand the syntax, you can just enter that yourself by text. Okay, it's already 6 in Paris, so I'll give you again 15 minutes to complete part 2. I'll post a little message there. Please let me know when you finished part 1, extracting information, which is so you're going to be doing that, going a bit further, doing the taint, going a bit further, search in memory. There's a little bit of Python. Remember, Control Enter, execute something. And the second cell, there's an invalid syntax because that's the fill in the blanks that I told you about. You should, there's something that you need to enter here, just so you know what you're executing here and not just blindly executing it. Please look at the Python if you're interested in, but yeah, just to demonstrate things. And please tell me when you finish part 1D. As I said in the message, part 1E is really the power taint, so that's kind of optional and something we can skip if not everybody is on the same page. And then when that's on, we'll move on to the next exercise. So 15 minutes at 15:15, we'll think again. If enough people have +1, please give me a thumbs up when you do that message when you finish the part. That really helps. Otherwise, I'll just keep waiting for nothing. Trace, let me go back there. Okay, so that was our taint. That was our taint, and you see there's a big transition gap here because we just moved back to our process. At the bottom of the trace here, we have a small status bar, which displays the current process, current symbol, and current binary, and along with some more information that you can actually copy paste things there. If you right click, you can copy any piece of information that's accessible there. So you'll see that I'm in my program here, and I am back in my program, even though if I clicked on in the middle, I would have jumped in somewhere else. So there, the taint just allows me to skip 300K instructions. And I am back here. And if you look at that, my source here is RAX. So that means that RAX there comes from my A to I. So that value comes from that A to I call, which we made earlier. So that's an interesting piece of information. Usually when you see RAX pop up in the widget, that's interesting information because it might mean this is the return value of something. Not always, but sometimes. So that's interesting. If we actually go up, we end up inside there. And again, what we should see, we should actually, the taint should just show, that the taint goes through the string conversion process. So it's able to go through that and actually all the way up to there. And if we see the state of the taint, so that checkbox here allows me to see what is currently tainted. At this selected instruction, you'll see that at the very beginning of my program, I have a memory region that's tainted. And if we open it up and open up as bytes, because otherwise it overlaps, this is very strictly the input string that we had, which is actually saw through one of the arguments here. So the taint was able to go from the crash to the very beginning of the trace to the input string that I passed to the program. So that's, again, that's how the string works, and it's able to go through things. And there are things it cannot do. That, I mean, there is a very definite perimeter of what the taint can or cannot do. Namely, it taints the data flow. But if your data flow depends on something happening in the control flow, like a jump or something, the taint will not be able to follow that. So it might need manual operations to help it go further. But for many cases, it just works, and it allows you to go back in your trace and get a super quick answer for that. We were using that in the next exercise as well. So I wanted you to see that using the taint and get super quick answers. What's going on? And at the very beginning, that's what I showed you earlier. This is this is how the value gets transformed to a 0, and you can see what's going on in the program and why there's a problem, because we overflow here. We just drop the f, and so that value becomes 0. So you should have seen that pretty easily there. The one other part of the exercise, and that's kind of a weird thing, so don't worry if you didn't exactly understand what I was asking for. You see in the frame buffer, before I recorded that execution here, I had made a couple of other executions in the virtual machine that I did not record, but we still have the output because it was in the same window. And in particular, we see that the program does check against bad values somehow. And one of the assumptions I want to use for that exercise is that this value is actually checked against hard-coded values. So the question there becomes, and the question I want you to see we can answer is, can we find values being used somewhere in the trace? And the answer is, if they go through memory, then yes, we can find them. If it only appears in the register, we can't because we don't index that. But if it appears in the memory, it's easy to just say, look for a certain value in the entire space of memory that is accessed at one point. And that's what the next part of the lab does. It allows you to do that. So that's what the script does, because this is the feature that's accessible through the GUI here. And that's the value we want to place. And the value we want to check for is 16381. So let me do that, 16381. That's the value I want to search for, because I want to see whether this value appears somewhere in my trace. And if it does, that's because I checked against it. And so that will help me locate the region of the code where I do checks against something. So I do that, I Control Enter or Shift Enter apparently on Mac. And I have a couple of values. So that value appears a couple of times. First, it's loaded into a register, and then it's used somehow to do something. So let's look at both. So I click there. It's synchronized so that I'm there. And so move RAX. So it's moved again somewhere else. And the second time I did charm. And yeah, now there's a comparison. So I have my value in RAX there, and I have the input value. I think that's the input value, and that's the checked value. And I can actually see that because I can look at the registers in decimal because I'm using the default build. This time I'm not forgetting. And this is the value that, yeah, RX is the value I'm checking against. And in that case, this is the value which I entered at the beginning. So that's the function that does the comparison, that checks against bad value. It's called goal value. So that was pretty easy to find. I could have also found that, and you might have done that, if I tainted the input forward, as I mentioned in the slides, we would have found one of the childs and a location of interest being that quad function. I think we can actually do that super quick if we go back to the very beginning there, go there and taint the input like so, super quick, boom, and forward this time, taint, and let me show you. Let me see the symbols, and we should see quad value appearing somewhere. Augment value, it's converted. No, why am I not seeing it? It's copied over. Yeah, it's copied way too much. Okay, I'm taking too long here. Yeah, quad value, there we go. So that appears. That piece of code appears, but of course, since it's been copied and manipulated and all that, there's a lot of results. So usually you want to try to get closer to your interesting point, like maybe tainting the return of A to I would have been a better choice here, because I would have had less code executing and less noise in my results. You have a question? Does the Python API allow us to do like regex checks. For that feature that we're talking about, no. Let me think. No, this is only going to work for actual values, not regex checks there. But that would probably be doable, to be honest. We haven't implemented it, but that would probably be doable, because what we do there is just what we have indexed are the regions of memory which are accessed, but we don't do anything else. So that probably would be a good feature to add later on in the product, I think. Okay, cool. Okay, so that's it for this exercise. Again, yeah, checking values that you build against hard-coded values is probably a very bad idea. So that's just built for me to show you things about REVEN. The next exercise, though, you will access by going over to the CVE notebook here. Dark mode, yeah. Oh yeah, I would love so. I would love that. Right now, it's dependent on your desktop's thing, and since we're using it through VNC, this is the only mode that we have. But yeah, we're thinking about it. Thank you for pushing that. It gives us more motivation to do these kind of things. Yeah, it's in our to-do list, absolutely. So yeah, sorry, time is moving fast. So let's head over to the second exercise. And now things I want to show you. So again, change the notebook, go to that different notebook, and to access the trace, please follow along. Everybody, please look at my screen. You need to do something. You need to go to File, Connect, and then select port 1338. This is by default your trace is at, currently you're looking at 1337, and we are just having that second trace on a different port. So connect, and you will be connecting to the next trace. And there are actually two traces here, 1338 and 1339, but you shouldn't have to connect to the GUI with the GUI to 1339. It's just through Python. So again, File, Connect, 1338, connect. And yeah, it doesn't allow because I'm already there. So that's your trace, and that's your notebook. Okay, hopefully everybody got that right. So that trace is a real thing. It's a real thing. First of all, the first difference that we see here is that I am not in some nice place. The trace did not start at the start of the program, because what I did here to recall that, this was a bug in TCP IP. So what I did was just start recording. I was in the middle of nowhere, that's what we see here, and then push the packet from the outside of the virtual machine, and that triggered the crash. But there's no way for me to start exactly when I receive my packet, or at least not right now. So what we have, the start of our trace is just not something we can exploit directly. We need to find that entry point in our trace. We need to find where to start from within here. If you look towards there, you'll see that our trace is not that big. It's about 5 million instructions. That's a very small trace by REVEN standards, but of course that's a lot of instruction to look at. So we still need to find that entry point. Hopefully what we'll get is a blue screen if we look towards the end of our trace, because that's an always crash. So it's super easy for me to use that blue screen as we did last week. Just by looking at the backtrace, you will find the KE bug check hex call, or you can find it just by going over there and TOS kernel and KE bug check X, find it and press F4 or click on next, and you will be exactly at the symbol that the system finally calls when there's an exception from within kernel mode. D8 debugging with REVEN hasn't been done. What is D8? Sorry, if you can give me more context about your question. V8, yeah, you can run Chrome and debug that if you want. Yeah, absolutely. You will see the code being created in memory, compiled there and JITted there. Yeah, sorry, I was looking for that word, and yeah, it absolutely works. Can you merge the binary and symbol inputs? Sorry, I don't understand. Like, you mostly search by symbol. Yeah, I search by symbol. If you want to look for an address in you can. So you have multiple options for search. You can search for a symbol within a binary, or you can just search for a binary being executed. So obviously that will be a lot of results there. But in my earlier trace, I could have searched for my program and I would have had a manageable amount of results. And I can also search by direct address. So like if I'm looking for that particular address and I know which it is for reasons, I can just look for it and I will get a result. Does that cover your question? Which Wiz J? I don't know how you're supposed to pronounce your username. Yeah. Okay. Cool. Perfect. So yeah, I have a bug check. So yeah, I must be faster than I am today. So KE bug check. So that's called in the end. But if we look up the backtrace for colors, we'll get some context about what's going on. And in particular, I have a security check cookie that fails, and so in the end, it ends up calling the blue screen. So my bug is here. I have a security check cookie that fails. Okay. A security check cookie, just for those of you who might not have the context here, is just a value that I placed somewhere in my stack, earlier in my stack. And it's basically it's a hard to build value somehow, at least for an attacker point of view. And if that value gets overwritten, then during the prologue of the function, so at the end of the function, I will check my security cookie. So when I enter a function, I write the security cookie, I do things, and when I exit, I check that the value hasn't changed. And if it does, there's an error because my stack has been overwritten, and that's a bug. So that's what we have here. That cookie here gets overwritten, has been overwritten somewhere. So it's fetched there or there. I think that's where my cookie is. Yeah, RBP plus something. That's my cookie, and that's the value it should have had here. And I do a comparison between the two, and it failed. So boom, I have an issue inside my kernel and a blue screen. So that's your starting point, how you will start looking at things with your trace. And I think it's pretty obvious right now that how you can actually get answers about who overwrote that cookie. That's something that's super easy to see with REVEN. So you will do that. But how to start? Just click, either look for KE bug check or just click anywhere. Oh, there you go. Click anywhere towards the end of the trace and look up the backtrace. So look up the backtrace for the symbol KE bug check, and even better for the symbol raise security check failure called by security check cookie. This is how you will start here. Yeah, the memhist, just to remember, so the security check key is not the value based on the RIP, but the value on the stack, so on RBP. And if you don't remember, this is how you show the access of history. And by default, we select the closest access or the current access. And so if I'm here, what I see is the right, but if I'm here, the previous access is the right. So I can double click there and get access to the right. And I already placed a bookmark here. Okay, 33, again, 15 minutes to move forward with the exercise, and we'll sync at 10 to 7 here in Paris. For the moment, I'll finish that first part and spoil a little bit the next part, so you have an idea of what's going on for those of you who can't stick around. But in any case, you'll still be able to look at exactly what we're doing here. All right, so you've had that trace there. And the exercise should take you up to at least a certain understanding of the crash. So we were there. If you remember, we had a cookie and it was overwritten. So let's look at where it is overwritten. I'm not using the taint here. I'm just using the memory history because I don't want to see where that value is coming from. I just want to see where it gets overwritten. I have a buffer, it gets overwritten. I want to see what code does that. And the code that does that is memcopy. So I have a loop there. I am inside the loop to memcopy, and I see that it's going to overwrite things, blah, 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 and moving up. So, what I'm going to do is not assume that memcopy has a bug, but rather look at what I am calling memcopy with. Okay, who is calling memcopy? This is Andy's get data buffer. So, it's doing something with the input buffer, which makes sense. Again, I recorded that by pushing a packet to that VM, and I want to look at the argument. So we have to keep track of the address there. That's my address as well, which is here. And looking at the memcopy and the CPU arguments. Let me push that down there. And can I just, no, yeah, okay, perfect. And my arguments is, yeah, let's go back to hex. RCX is the destination, and my destination is indeed 6370 something, and the value, so that's destination source, and that's going to be the size, and the size is 0x30, so I'm going to go up to 780 hex, so that is past my cookie. So indeed, the arguments I'm passing here are all wrong, and there's a problem there. So that's what the exercise hints you at, I think. And then from the call to end this gate data buffer, we can try look at the arguments to end this gate data buffer as well. And if you look at them, because I think there are, let me blah blah blah. Where was I? Preliminary analysis. Okay, so you get the prototype of that function, and you get the buffers and the storage and the I think the second argument is the size to read. And if we look at the second argument that's my size, and the third argument. So here that's my destination buffer. And if you look at that, this is again going to go past the value that I am interested in. Again, and this get data buffer is not responsible for the bug. The caller to that just instructed that function to override the buffer. So we need to move up again and try to understand what's going on here. So a couple of ways we can go starting from here. Either the size of the allocation is too small, or the which we did when we got the address, or the size that we're trying to write is too big compared to what the buffer should be. And we are going to make an assumption here, and that's the size that we passed is too large. You can check the other two by just going back further in the tape, but we're going to assume that the size is too large. So we want to see where that size is coming from, and that's when we are using the tape, because we want to understand what the parameter, how it's built, where it's coming from, all of that. So at that point, we taint RDX from there. Current transition, backwards, go. And we will see it's coming from here. And at that point, R15 is, that value is again the same, so that's okay. And here, R15 is, yeah, it's coming from here. There, and if we look at the symbols, actually, we will see that this is coming from the packet. So at that point, it's more interesting. We have CX read there, which is written into something. So let's look at that. No, that's not interesting yet. Where is it? Is it here? I'm looking actually for the data packet, which we have. Yeah, I think that's interesting. So I'll be taking a few shortcuts here to make it quicker for you to understand. But at that point on, this is actually, you see, this is coming from NetIO, so it's coming from the network. I could have seen that as well if I had extracted the PK file from the trace. It would have made the connection more obvious. Which address correspond to a packet at which point in time. But just take my word for it for the moment. This is a packet file which we received, and those are actually type size value. So this is the type of the buffer that we're going to have, and this is the size, and this is the content. And again, here what we have, the 22 here, that which we are reading, RCX, and then multiplying by 3. So we have our 110 hex that we saw in the function earlier, is actually coming straight from there. Okay, so that's a value and that's a type. Okay, and the thing is that we have, so the size that was too big was actually coming from the packet. So if this size is too big here, it's going to crash. If the size is smaller than the allocation, I don't remember exactly what the allocation allows for, we are not going to have a crash. Okay, so that's one very interesting result. We were able to locate to connect our crash to a problematic value in our packet. And I think that's where the exercise stops. But that's not the whole story. And the thing is, with REVEN, you can get super interesting answers about things like that and code location and all of that. But when there's some kind of logic bug, it's less obvious to see. Then for that, you need to fall over to regular static analysis, because REVEN is not everything. It's one tool in the toolbox. So at that point on in your analysis, if you were approaching that problem with zero knowledge, you would need to head over to static analysis and try to understand what's going on. And what you would see at that point is that, and I'm spoiling the next part here, what you would see is that, so yeah, this is interpreted as a value, but you should not be going down that path at all, reading that value here, reading that portion of the buffer as a type size value. You should not be doing that. And that's because there's an error somewhere else that allows that code path to be actually executed at all. And the problem lies rather not with that value, but with this one. What we have here, if you look at the packet definition and all that, you will see that we have a value here, which a type here, whose size is supposed to be odd and not even. And here, since we have an even thing, but an odd number of value afterwards, it's going to, fail and somehow and just start interpreting the content of that packet as a new data packet, something like that. And so that's why we hit that code path. And there's no check at that point, because all the checks on whether the values are are big enough or small enough or all that occurs beforehand in the code. Okay, so that's what the exercise tells you. The next part. We have our packet here, and actually Wireshark does show you that portion as part of that option here. Yeah, it's not a packet, it's just a part of the packet. And the type here is 19, and we have 04, and we should interpret that as the content of that value and not a new packet. Okay, so that's what the bug is, and that's something you do not find with REVEN, although you have a lot of hints at that point to try and understand what's going on. And what the second part of the exercise does, and that's what we're going to have a look at after, is looking at the problem. And actually, I can show you that super quick. Looking at the problem. So what we did, the next trace, the 1339 that you can connect to, or that I'm just connecting here via Python, is the patched version. So we just make the same trace with the same packet, but with the patched version of Windows. And we can compare the two to understand what's going on. But instead of just comparing all the instructions, in that case of the call to IPv6 handle route to advertisement, I'm not going to taint all the. I'm not going to compare all the instructions. We are going to taint the input values, the input buffer that we saw here, and that's offset 10 actually, because that's the start of my packets, and that's offset 10. And we are going to taint byte by byte and do the comparison of the taint results. So that's what I'm doing here. I'm tainting the first value, that's the type. So I'm tainting the type and comparing whether or not there are differences. And you will see that there are not many differences here. The addresses look very similar, although of course the string that looks similar, but of course the addresses are slightly different. But then there's an early exit of the function, because the right is the trace where the bug is fixed. And if you look finally at the second value, which is the size, which is we know the problem is, because I just spoiled you, then we will see that to the right there is a new piece of code, and that actually checks the oddness of the initial parameter on a rather convoluted way, because at that point that value has been multiplied by 4 or 8 multiplied by 8. So, but it's actually checking the oddness or the evenness of the initial value, and that's something that's super easy to see there. Because we're not comparing everything, but just the 10 results. So that's the final thing I wanted you to see, and because it's just, I think it's a rather different way of looking at things, and yeah, that REVEN can provide super easily. Wrapping up, yeah, and that's it. So again, we are going to stay a little while, but for those of you who don't have the time for that, this lab is now over, and you have, hopefully at that point, you have some experience with the product, you've touched it, you know that it's real, and you have an idea of maybe how you could use it. So if you want to buy the product, that's the little bonus for the end. We are offering a 30% coupon of a professional license up until the 16th of April. Maybe I'll copy paste that coupon over to the chat. Oh, Mark is doing that. Thank you, Mark, I guess. And so yeah, thanks. But thank you so much for joining today's lab. I really hope you learned something. I really hope it was enjoyable. I really hope it fit what you expected and what you expected. And through these exercises, you got to get a feeling of what this timeless debugging and analysis thing is about. We have a little survey because we are super interested in your opinion about this lab, about the content, about the form that it took. So that's the message that Mark just posted. Yeah, please fill in that form. This is super valuable information for us, super interesting feedback, because this is how we get to improve every time we do something like that. So yeah, please fill in that form. It's going to take a minute. Just click, and that's done. And again, if you're interested, you have a coupon if you want to buy the product. I'll paste the coupon as soon as I'm finished talking. And otherwise, get in touch if if you're interested in sales or stuff like that. Yes, okay. Thank you, Mark, again for posting that thing. Was there around? I think I've showed you everything I wanted to show you, so I'll stop the session here. But we will stay around in the chat, so feel free to keep working on the exercises. If you have questions, last question for the end, now is the right time because I'm still there, so yeah, I can address them orally. Otherwise, I'll stop the session, and yeah, we'll stick around. The VM stay up, and don't hesitate to get in touch with us. We have contact@tetrane.com. That's our email. I'm at MFAVREAUX on Twitter. I think I posted that at the very beginning. So you can reach out to me directly, or at Tetrane as well. And yeah, I hope you enjoyed this lab, and thank you so much for your participation today. I hope you enjoyed it, and I'll see you hopefully sometimes in the future in for real, and not without a lockdown, because where I live in France, the lockdown has come back. So see you all. In any case, have a great weekend and a great end of day, and bye. See you next time.